Early in this unit, I described a mechanical wave as the propagation of energy through an elastic medium. Well, exactly how much energy? What we're going to take a look here is the energy that is transported by a one-dimensional simple periodic wave. That is a simple periodic wave that is propagating through a one-dimensional medium. Okay, so we have a simple periodic wave propagating through a one-dimensional medium. Okay, so let's say that right here I have a simple periodic wave like so. It's propagating in this direction with some speed v. Okay, let's assume that there's somebody, for example, over here holding on to the spring like so, and this person is just oscillating the spring up and down like so in simple harmonic motion, causing the propagation of these waves. We're going to think of this person as a transmitter. Okay, and then over here some distance away, this person over here, we'll say, is going to receive those waves. We'll think of that person as a receiver. As we run through this calculation, we're going to assume that there is no heat loss. We'll assume that there is no damping. We'll assume that there is no friction associated with the ground. So then therefore, the amount of energy per second that this person transmits is exactly the same as the amount of energy per second that this person receives. So once again, we'll assume no heat loss. Okay, what we're going to do is we're going to derive an expression for the power transmitted, the amount of energy per second that is propagating through this medium. This is the energy per second that this person uses to transport these waves. This is the amount of energy per second that this person receives over here on the other side. Okay, now there are some properties associated with these waves, that, for example, the transmitter can control. The transmitter can control the frequency of the waves. This is just simply how many times per second the person oscillates their hand back and forth, and they can also control the amplitude of these waves. The speed of the waves themselves, if you recall from the previous lecture on wave dynamics, is governed by how much tension is applied to the medium and the linear mass density, mass over length, which is the quantity mu. Okay, now what we do is we take a look at a small section of spring, like so. This right here is a small section of spring that has a mass delta m associated with it. It has a length delta L associated with it. And this small section of spring right here is in simple harmonic motion. Recall that the total energy E of a simple harmonic oscillator is 1/2 Ka squared, where K is the spring constant. Now, when I say spring constant, I'm talking about an imaginary spring constant associated with this section here of the medium as it oscillates up and down in simple harmonic motion. Now, basically what I have to do is take this expression and essentially just rewrite it. I need to write it in terms of quantities that are associated with simple periodic waves. So then therefore, let's get rid of the spring constant K. We'll do so by using the following expression, if you recall, from simple harmonic motion. From simple harmonic motion, recall that the angular frequency of the oscillation is the square root of K divided by the mass delta M. So what I'm going to do is just a little bit of math here and then solve for K and then plug it here into this expression. So let's go ahead and get rid of, first of all, the radical sign. I'll square both sides of the expression like so. Okay, move the delta M here to the other side, like so. And then this expression right here is the spring constant K. Let's go ahead and plug that into here. Like so. Okay, next let's get rid of the omega. Instead of writing this in terms of angular frequency omega, we're going to do so in terms of frequency small f, which I've already written on the board. Recall that the angular frequency omega is 2 pi times the frequency. Let's go ahead and substitute that into here. Like so. So notice what I did. I squared the omega, so 2 squared is 4, pi squared, f squared, like so. Let's go ahead and cancel out a 2. Like so. Okay, the next thing to get rid of is the mass delta M. This is where the density comes into play once again. So recall that density is mass over length. So then therefore the mass is equal to the density times the length. Let's go ahead and plug that into here. Like so. And now the last step of this expression here, or the last step in this derivation, is to take this expression for the energy E and divide out by the time delta T. What we want to do is describe this now in terms of power. This then gives us the amount of energy per second that is being transmitted by the transmitter, or equivalently, the amount of energy per second that is being received by the receiver. So we're going to turn this into a power calculation. Okay, now recall that power is energy divided by time. So we're going to take this expression here, this rather complicated string of terms, as you can see, and then we're going to divide it by a time, which we'll just refer to here as delta t. And then this right here is distance divided by time. This is equal to the speeds of the waves v. That then gives us this expression here. Like so. This expression here describes the amount of energy per second that is being transmitted by the transmitter. Equivalently, it's the amount of energy per second that the person is using to oscillate the spring up and down. And then if we assume that there is no heat loss, this is also equivalent then to the amount of energy per second that is being received by the receiver. Once again, this is assuming no damping and friction and so on and so forth. Using this expression, however, is actually quite easy. The hard part about the expression is just remembering it. So let's go ahead and do a simple example here. Okay, I'm going to do some erasing. I don't need the derivation at this point, of course, so let's just go ahead and get rid of that. Okay, and then let's go ahead and take a look at the following problem. As always, please copy it down into your notes as I read it here. Okay, a spring has a linear density of 0.5 kilograms per meter. So we're given the density is 0.5 kilograms per meter. And the tension that is applied to the spring is 10 newtons. That's a couple of pounds of force. So the tension, capital T, is 10 newtons. How much energy per second, in other words, a power calculation, is needed to transmit simple periodic waves with a frequency of 3 hertz? So the person is moving their hand rapidly back and forth. The frequency is 3 hertz. And the person then creates these waves with an amplitude of 20 centimeters, 0.2 meters. Okay, essentially what we have to do here to calculate the power transmitted is a 2-step calculation. The first thing to do is to calculate the speeds of the waves v based upon this expression here. So let's go ahead and do that. So the speed, very simply, is now the square root of 10 newtons and then divided by 0.5. There we go. And this works out to be about 4.47 or so meters per second. This is a typical number when you're talking about waves, for example, propagating through a spring. Okay, now that I have that speed, let's go ahead and calculate what I'm going to refer now to as P transmit. So this is the amount of energy per second in terms of watts that is being transmitted by the transmitter, the person over here on the left-hand side of the diagram. In order to make that calculation, we just plug everything here into the expression. So I've got the V still here in my calculator, so I'll leave that, and then times 2, times pi squared, times the frequency squared, times the amplitude squared, and then times the density of a 0.5 kilogram per meter. And after all of that, I end up with an answer here of about 16 or so watts. So what I'm calling here P transmit is equal to 16 watts. So in other words, it costs the person, if you will, 16 joules of energy per second to transmit these waves. If we assume that there is no heat loss, this is also equal to the energy per second that is received by the person on the other side of the diagram. This has to do with the last portion of the problem. Let me move my file. Okay, so the last portion of the problem asks the following. how much energy is received after 60 seconds by a receiver, assuming that no damping occurs. So now what we'll do is we'll take P receive here, and we're going to set it equal to the energy received per time. And then what we're given here in the problem is that the time is 60 seconds. So as these waves then come into the receiver continuously over the course of 60 seconds, how much total energy does that person receive? So then therefore, the energy that's received, very simply, is going to be P receive multiplied by time T. So just take the roughly 16 watts that we have on the top board and multiply it by 60, and this comes out to be about 953 or so joules, like so. So deriving the expression for power, as you saw, involves a string of terms. Probably the hardest part about the expression is just remembering it, but using it, however, in an example such as this is quite straightforward.